Okay, let's start class. So from today, we will talk about unsupervised learning. We've already finished the supervised learning. We covered start from the introduction to the statistical learning, then talk about the uh, smoothing, non-parametric smoothings, and talk about the generalized additive models, then followed by the classification and the regression trees. Then move to the ensemble learning. We talk about the baggings and the random forest. And at the end, we talk about the artificial neural network. These are the supervised learnings. Now we will talk about three topics for the unsupervised learning. The first one is the cluster analysis. The second one is the principal component analysis. And the last one is the market basket analysis, which is the association rule mindings. Okay, so these are the topics for this course, and for the in the Moodle, I've already posted the announcement for the final exams. So the final exam will be on the December 9th, from 7:30 in the morning to 9:30. Okay, so that will be the in person, and I will tell you the room number later. And the final exam will be comprehensive. It only contains two types of questions. One is the multiple choice, one is the true and false. And I've already posted some sample questions in the for the final exams in the Moodles. Don't work on that, just take a look. And I would say you, after you prepared, reviewed all the materials, then you can try the sample questions. I will post it the solutions for the sample questions later, so you can get some feelings about the difficulty levels. And most all these questions are mainly the conceptual questions. You would you should bring the calculator, but the calculation is very minimal. Most of these are just the test you if you know the knowledge or not. And for the final project presentation, I've already sent out the announcement last week. So and already I think 4 or 5 of you have already volunteered to present on December 2nd. And also I have some space available for December 2nd and December 4th. So if you want to volunteer, just let me know. And as I said, if you volunteer to present on 2nd or the 4th, you will get some bonus points for the final project presentations. And that's the plan. So I will finish the materials and you will do the presentation in the last week of the class, and then we will have the final exam. So this is the plan. Any questions? Okay. If you don't have any question, let's start today's material. So we will talk about cluster analysis. So supervised and unsupervised. Supervised learning, we know that the data contains two parts. One is the input variable, right? So we have the x1, x2 through xp. These are the p variables. And we should have at least one response variable, right? But some data set may contain more than one. Remember the case study to predict the algae blooms? So we can have more than one response variable, but most of the time we just have one. So that's called a supervised learning, because the response variable functions as a supervisor to evaluate how good the model is, right? So the purpose is to predict the Y using all the input variables informations. And the supervised learning contains includes the regressions and the classifications, right? And not just these two, also it includes like rankings, but we didn't talk about rankings here. Mm. For the unsupervised learnings, the data only includes the predictors, x1s through xp's. So we don't have a particular supervisor response variable here. And the goal is not to do the prediction, but to discover something interesting and something unknown before about the data, right? For example, if we can uh, identify some particular patterns among the subjects, right? Is there any cluster patterns? Is there any grouping of the variables? And these are the, or is there any subgroups and these things? And we will see some examples uh, later. And another is, can we visualize the high dimensional data, which usually very hard to see the interrelationship among the samples for the high dimensional data in the low dimension way. Okay, so that is also a very important applications. So we can reduce the dimensions and then we can have a good way to visualize the data. And for the unsupervised learnings that include like the vector quantization. So this is a useful method to reduce the dimensions, to visualize the data, and also to reduce the storage of the data. And the PCAs is an important dimension reduction method and also a data visualization method. For the cluster analysis can be used to identify the, the patterns among the subjects and variables, and especially those clustering patterns. And the self-organization maps is an algorithm to visualize the high dimensional data in low dimensions. Okay, so and there are many other methods. Okay, but here, cluster analysis is usually more difficult than the, I mean, unsupervised learning problems are usually more difficult than the supervised learning method. Why? Because we don't have such a gold standard. We don't have a response variable. So we don't have a supervisor here. So usually the unsupervised learning are very subjective, especially for the cluster analysis. It's very, very subjective. Like here, I'm showing some of these uh, characters in the Simpsons families. Like if I want you to do the cluster analysis, we can cluster in many different ways. For example, we can cluster these characters in as the left hand side ways. So we can cluster the Simpsons family members as one group, and the school employees as another group, right? And we can cluster based on the genders, females and males, and these. So which one is correct? Since there's no response variable, so it's really subjective. So that is really based on the investigator's research purpose. Okay, so central to all the goals for the cluster analysis is the notion of the how do we quantify the similarities or the dissimilarity or the distance between the subjects. Okay, so to identify what is the definition for the similarity or or the distance, that is very important in the cluster analysis. Okay? So regarding the methods, there were two types. One is actually there was three types. One is the partitional methods. So the partitional methods is to divide all the subjects into non-overlapping groups, clusters we call it, such as the K-memes, K-medoids. So these are the popular partitional methods. Like here, on the right-hand side, you can see these are the partitional methods. And there are another type called hierarchical method. It's not giving you the non-overlapping group, but as like a tree diagrams. So this gives you a set of nested clusters organized like a tree diagrams. And for the hierarchical method, there are two types. One is the bottom-up approach called agglomerative approach from the bottom and merge to finally to merge to one group. So that's the bottom-up approach. And there's another approach called a top-down approach, also called a divisive approach. So start as a one group and then divide until every single subject is its own group. Okay, so, and there's another type that's called a model-based clustering. And we will talk about all three types. Okay. Okay. As I mentioned, the most important part for the cluster analysis is really how do we measure the dissimilarity in the cluster. Okay. So sometimes the data is represented directly in terms of the dissimilarities or the similarities. We will see some examples in a few minutes. Okay. But sometimes they do not. Okay, so we have to find a way to quantify the dissimilarity or the similarity or the distance. They are essentially closely related. Okay, so dissimilarity metric is expressed in terms of a distance function, which is typically a metric. So as a metric, so that one of the properties is it's symmetric. So that means the dij equals to dji. So the distance between I and j is the same as the distance between j and I. Okay, so there's no direction. So it's symmetric. And the second is the dii is equals to zero. So the distance to itself is always considered as zero. Okay, so if the metric that we found is not symmetric, that's fine. We can easily create a symmetric metric by replacing the D by the D plus D transpose divided by 2. So D is a distance matrix if it's not symmetric. So a, a matrix, if it's not symmetric, that means the ith row, jth column elements is not the same as the jth row, ith column elements. If they are not the same, then it's not symmetric. Otherwise, it's symmetric. If it's not symmetric, we can always have the D distance matrix D plus the transpose of distance matrix D and divide by 2. Okay, so that will become a symmetric metric. And for the dissimilarity based on the x1 through xp, we can write as the dxi comma xk equals to, so here the subscript I and k are the index for the subjects, okay, is equals to the summation of wj, that's the weights for the jth variable, okay? So j is the index for the variable times the dj, xij, and xkj, okay? So the dissimilarity usually can be defined as a weighted sum of all the variables if we have more than one variables in the data, okay? And the weight is the wj, and for each variable, we also need to define what is the distance for that variable, okay? So what are the choice for the dj? If it's numeric, that's relatively easy to define. So we can use like a squared distance. So the dj equals to the square distance, okay? So the square distance put more emphasis on the large distance compared to the smaller distance. Why? Because the large distance, if we take the square, that will be even larger, right? Let's say the distance, if x1 minus x2 equals to 10, okay? And there's another one, x1 minus x3 equals to 1, okay? So you can see the difference is just 10 times. But when we take the square, if we use the square distance, that will be 100, is that right? And that still be 1, so that will be 100 times. So if we use the square distance, it really put more emphasis on those large difference than the small ones, okay? So, and also we can use the correlations, okay? So we can find out the correlations. For the correlations, if the inputs are standardized, okay, then we will prove that the correlation distance is equivalent to the square distance. Okay, so here the assumption is if the inputs are standardized, so that means all the variables have the zero mean and the variance is 1. If that is the case, if you use the correlation as a metric or using the square distance, they are equivalent. Okay, otherwise they are not. Okay. So one good thing for the correlation matrix is that it's not just for one variable, it's for all the variables. Okay, it used all the variables, not like the square distance. Okay, and of course you can use the Euclidean distance. That's the square root of the squared distance for more than one variables. Okay, so Euclidean distance is another choice, and also we can use the absolute error. Absolute error is just there is a typo, so here is it should be xij minus xkj, and also here is xij not comma, it should be minus. These are the typos. Okay, let me just remove that and rewrite. So it should be minus here, and also it should be minus here. Okay, so absolute error is similar to the square distance, but it's more robust to those outliers. Okay, because it didn't take the square. Okay, so these are the common choice for the distance matrix functions for the numeric variables. But what if the variable is categorical, right? So if it's categorical, then let's say we have m categories. Then we need an m by m distance matrix. Okay, so let's say, suppose we have a categorical categorical variable. Let's say x has 3 categories. Then we need to have a 3 by 3 matrix. Okay, and on the diagonals, it should be all 0, right? Because if the two subjects have the same categories, it should be considered as 0 distance, right? So what about this one? So it's category 1, 2, 3, and category 1, 2, 3. Okay, so this one is the distance between the category 1 and 2, so D1, 2, right? And this one is the D2, 3. That's the distance between category 2 and 3. And this is D2, 1. And this is D1, 3 and the D3, 2, right? But remember, we have a symmetric property. So D21, D12 should be the same, and D31, D13, and D32, D23 should be the same. Okay, so we need to have this m by m distance matrix defined. Okay, so these are the common choice for the distance, but that's not the only one. So you can define by your own. It's really, really based on the investigator's purpose. Okay, and usually different. If you use the distance matrix wisely, the cluster analysis can be very, very useful. But however, if you choose the distance matrix, distance function not wisely, the results from the cluster analysis can be actually misleading. So I will show you some example in a minute. And also, we have the weight function, right? Remember, we have the WJ. So how do we choose the weight? Okay, this is very useful, especially if we have some irrelevant variables in the data set. Okay, suppose we want to run a cluster analysis, and we have a data set that have 100 variables. If the investigator have a purpose, like they want to find out some cluster patterns among these patients. And if they know that some of these variables may be irrelevant variables to their purpose, so it's better to just remove these variables, or they can put them in a very small weights. Okay, so that is very, very important. Okay, but if you have no idea about which variable is relevant, which variables are not relevant, then you can choose the equal weights. So here, choosing the equal weights is kind of tricky, because if setting the equal weights WJ for each variable, that actually does not necessarily give all the attributes equal influence. Why? Because the X variables, they may have different means and variance, and so if you choose the same WJ, same value for all the WJ, they are still not equally weighted. So how to find the equal weights? So if the weight WJ is proportional to 1 over DJ, then that will be the equal influence. Okay, so what is DJ? DJ is the is the average distance for that particular variable, pairwise, average pairwise distance for the variable j. So how to find out the average pairwise distance for the variable j? It's just doing the double summation for the according to the variable j. So it's the double summation for the dj, xij, xkj. Okay, so here the k is from 1 through n and I is from 1 through n. And take all these, and you can see we have n times n terms, right? And divide by 1 over n squared. And that will be the overall average pairwise distance for the variable j. Okay, if we know the dj's for all the variables, and we choose the wj is proportional to 1 over inverse of the dj's, that will be the equal influence for each variable. Okay, so that's how do we choose the equal weights. uh, in general, if we set the wj to the inverse of the dj's, that is often recommended if we have no idea about which variable is important and which variable is not. Okay. And but if we have some prior knowledge, that's which variables are more relevant in separating the groups, then we should assign higher influence, more weights on these variables. Okay, so choosing an appropriate dissimilarity measure is far more important than the choice of the cluster method. So we will talk about several cluster analysis methods. Okay, and they can be partitional, hierarchical, model-based. But I tell you what, so the difference among these cluster analysis methods are trivial if compared with the difference that caused by using different dissimilarity measures. So choosing the appropriate dissimilarity measure is much, much more important in the cluster analysis. Okay, so it's, and then you may ask, so how should we choose that? It's really based on the investigator's purpose. Okay, the ones that I listed in the previous slides, these are the very common ones, but the one that the reason behind that you choose which is appropriate ones is really according to your research purpose. So we will see an example in a minute. So for the missing values, we can eliminate those observations with missing values. So that's the easiest one. But if the data set have lots of missing values, of course we cannot use that. So we can maybe impute the missing values by the means and medians, just like what we talked about in the case studies before. And for the categoricals, we can treat the missing value as a new category. And usually for the cluster analysis, if the variables are numeric, we tend to standardize the variables to mean 0 and variance is 1. Because if we don't do that, and if we forgot to assign the weights, then those variables that has higher variations has much more influence on the results, on the cluster results, compared to those variables has low variations. Okay? So now let's see an example. So this is an online shopping example. Suppose an online retailer interested in clustering the customers based on their past shopping experience. So the goal is to identify those subgroups of the similar shoppers so that the shoppers within each subgroup can be shown the items, ads, and coupons that are particularly likely to interest them. So if we have like this is the sample data set, let's say. So the data is in the form of a matrix where the rows are the shoppers and the columns are the items that they bought. Okay, so what type of dissimilarity measure should be used in the cluster analysis for this shopper? Okay, so if the Euclidean distance is used, then the shoppers who bought very few items, like the infrequent buyers like A and B, they bought just one items. Okay, but shopper C and D, they bought a large number of items. So of course, if we use the Euclidean distance, A and B will be clustered as one group, right? And the C and D will cluster as another group. Okay, but if we use the correlation-based distance, okay, then the shoppers with the similar preference will be clustered, right? So here, if we use the Euclideans, A and B will be together. Otherwise, for the correlation-based, C and D will be, because they have the similar performance. And you can probably see that more more clearly from this plot. So here we have three shoppers. So these horizontal axes are the variable index. Okay, and so we have the buyer one, 2, 3. Okay, so 1, 2, 3. So here you can see the buyer one and the buyer two. If you look at the buyer one and the buyer two, buyer one, the shape looks like that, which has a very similar shape to the buyer two. You see that? If we use the correlation, then what we will get is the buyer one and the buyer two. They will be clustered in the same group because they have the same shape. That's what the correlation analysis does. But if we use the Euclidean distance, then the buyer 1 and the buyer 3, these two will be clustered as one group because they both have lower values, so they will be very close together. So you can see using the correlation metric or using the Euclidean distance can be very different results. Okay, so that's give you some idea that if you choose the different metric, the results can be very different. So which one we should use, right? So let's see another example. So it's still based on the online shopping case, but this time, should we scale the variables to unit variance before the dissimilarity measure or not? Okay, and for the online shopping, some items may be bought more frequently than the others. For example, if we look at the socks, right? A shopper can buy 10 pairs of socks a year, but people buy computers in a much rare way, right? So we usually bought a new computer maybe 2 or 3 years, every 2 or 3 years. So high frequency boards like the socks will have a much larger effects on the inter-shopper dissimilarities and the results from the clustering if the metric that we used is based on the counts, right? If the variables are scaled to the unit variance, then each variable will in effect be given equal importance in the clusterings. Then the question is, what are the scales that we are scaling the variables? because we can do the scales based on the counts, like how many pairs of socks or how many computers, right? We can based on these counts. Another scale is the value, the price, right? So the amount of the monies. So here you can see on the left, this is the number of items that bought. So you can see the left-hand side, the left ones are the socks. So you can see the socks has much higher frequencies, but computers have much low frequencies, right? And here the center ones is scaled these number of items to the unit is 1, to the standard deviation is 1. Okay, and here the right one is not based on the counts. It's based on what? It's based on the dollars. It's the amount of monies that they paid. So you can see in that case, the computer is much, much bigger. The price for the computers is over $1,500, but while the socks is much lower. So you can see if we use this metric to do the cluster analysis, you can see actually the number of socks that the consumer bought has a dominant effect on the cluster results, right? But if we use the amount of monies, you can see the computer has a dominant effect, right? And if we standardize it based on the counts, they will have the equal importance. Like buying the socks and buying the computers have the equal importance. Okay, so as an investigator, you should ask the question to yourself. So if you are the manager, do you want to take the equal importance between the socks and the computers? Or you will have more importance on the computers than the socks, or more importance on the socks than the computers, right? Because different decisions lead to different metric. But if you don't care about this and just randomly select one, so the conclusion that you got, which you may not aware, can give you misleading results. Because let's say if you really care about the amount of monies, right? Because that is directly related to the benefit. Okay. So in that way, so that's directly related to the profit that you earned from this business. So in that case, you should use the amount of money as the scales. But if you accidentally choose the first one, and the cluster analysis gives you the results, gives you the report, actually is put much more importance based on the socks, then that is not really what you need, what you want, right? So these results is very misleading. So that's why you have to choose these metric very, very carefully, because that is directly related to the quality of the results from the analysis. Okay, any questions so far? Okay, if you don't have any questions, let's talk about start to talk about the cluster analysis methods. So first, we will talk about the partitional method. So the k-means is one of the most popular iterative descent clustering methods for partitioning the data set into k non-overlapping clusters. So to perform the k-means clustering, we have to specify the desired numbers. So the K means K is the number of clusters. So that has to be specified by the users. Okay, so given the K, then the algorithm can run. Okay, so if let's say we set the K is 2 and we run the K-means, you can see this is the cluster results. If it's 3, this is the results. So you can see compared with K equal to 2 and 3, you can see the main difference is that we have 2 subgroups here. But when the K is 2, they merge these 2 subgroups as one group, right? Okay. So for the K-means is 4, then we have uh, these 2 groups, but also we have this another group and the rest as this. So you can see if K is different, the cluster results are different. Okay? So the user need to specify the case. Okay, so how do we do the cluster analysis using the K-means? So this is an optimization problem. Okay, so the objective function that we want to minimize is the within cluster variation. Okay, so here the within cluster variation is defined as this one. So here the first summation is for the K is the index for the cluster. So we have K cluster. Okay, so lowercase a from 1 through uppercase K. So that's the number of cluster. And then within each cluster, okay, then we have 2 subjects, any 2 different subjects, I and I prime. And they both from the cluster K. Okay, and here we want to find out their summation for the squared distance. Okay, and this, if you take a close look, you can see it's not difficult to find out this is equivalent to what. This is equivalent to this. So we can actually prove that. Okay, so this is mathematically equivalent to this. So what's the difference between these two? So we have 3 summations here, but now we just reduce to 2 summations. Okay, so instead of having double summation for all the subjects within the cluster K, we find out their squared distance. It's replaced by the NK. NK is the number of subjects in the K cluster times this. What is this? This is, in here we have a centroid. So the K, XK bar, that's the centroid for the K's cluster. Okay, so what is a centroid? Centroid means that for the cluster K, xk bar is equal to the mean for the x1 through xp using all the subjects in the cluster K. Is that clear? So the centroid for the K's cluster is the coordinates are equal to the average value based on all the samples in the cluster K. And that is called a centroid for the cluster K. Okay? So this is equivalent to the summation for all the cluster times the nk times this one. Okay, so I won't show you the proof, but this is mathematically equivalent, and we can based on the rigorous proof. So now we know that's why it's called k-means, because now it's related to the means. Centroid is the means, right? So to get the global optimal solution for the k-means cluster is very, very hard because that involves assignment of k or of n points. N is the total number of observations into k clusters. And that's to guarantee to get the global optimal solution that can only be achieved by exhaustive search. Okay, then you may ask how many search we will have. Okay, just give you some idea. If we just have a 25 observations, that's a very small sample size. 25 observation into 4 clusters. Okay, so we do cluster analysis. We define the k as 4 and the total sample size as 25. So how many options can we have? We will have 5 times 10 to the 13th. That's possible assignment. Even for such a simple small data, we will have so many possible assignment. So that's why in practice, it's very, very difficult to get the global, to guarantee to get the global optimal solution. Because we cannot do that. We cannot afford the exhaustive search. So the k-means used a greedy algorithm. Okay, so first is randomly assign each observation into one of the k clusters. And then we iterate until the cluster assignment stops changing. Okay, so step 2 is an iterative search. So for each of the k cluster, we compute the cluster centroid because we randomly assign, right? So after we assign, we can find out the centroid. How to find out the centroid? Very easy. That's just take the mean, right? If we have 3 observations in the centroid, in the cluster 1, we just average their values and get the centroid for the cluster 1, okay? And then we assign each observation to the cluster whose centroid is closest. So after we get the centroid for each cluster, then we reassign each observation to its closest centroid. Okay? And then we repeat step A and B again, because after we reassign, then we can update the centroid again. After we update the centroid, we can update assignment again. You see that? Until convergence. Okay, so that's just one batch based on a particular random assignment, initial assignment. Then to avoid the global, or to avoid the local minima, but we want to get the global minima, right? So what we need to do is we will do that initial random assignment multiple times. So each time we may achieve the different local minima, and then we choose the one that gives us the best results. So what is the best result? The best result is the one that gives us the smallest within cluster variation values. Okay, so that's the k-means clustering algorithms. Okay, so you can see the k-means clustering derives its name from the fact that in the step 2A, to get the cluster centroid are computed as the mean of the observation assigned to each cluster. So that's why it's called k-means. Okay, and each of the step 2A and 2B reduce the value of the within cluster variation so that the convergence is assured. Okay, so these iterations is very quick. Usually a few iterations, like 3, 4, 5 times will converge to the local minima. So what we do is this is very fast, Then we repeat that with different initial random assignment multiple times, okay, to avoid those local minimas, okay. Okay, so this is an illustration. So this is start from here. We have the original data set, okay. So let's say if the K is 3, okay. So here we start with the raw data, and then the first step is what? Random assignment. Since we have 3 clusters, okay, we pre-specify the K is 3. So we just randomly assign each observation into one of the 3 groups. So we have the green group, the yellow group, and the purple group. Okay, so these are the step 1 is the random assignment. And the iteration 1 for the step 2A is what? Is to find out the centroid. You see that? So you can see these are the 3 centroids, very close. Why they are very close? Because that's based on the random assignment. Does that make sense? Because we just randomly assign. So it should be very close, right? So these are the 3 centroids, 1 for each group. And then what we do is, in the step 2B, we reassign the subjects that is to the closest centroid. Like here, why all these samples becomes yellow now? You see, here they are mixed. Why these become yellow? Because all these observations are closest to what? To this centroid. They are all closest to this centroid. And this centroid is initially assigned as yellow. So they all becomes yellow. Does that make sense? And all of these becomes purple, and all of these becomes green. So we reassign this membership for each observation. Membership is defined by choose the one that choose the closest centroid. And then we repeat the step 2A in the iteration 2, right? So now this time we updated the centroid. Now this time you can see the centroid becomes far apart. Now this is the centroid for the red, yellow group. This is purple group, green group, right? And then that's 2A. We updated the centroid, and this time we reassign to the closest. And usually it converges very quickly in a few iterations. It converges. What does convergence mean? Convergence means when there's no change of the membership, then it's converged, right? Okay, then that's one batch. That is based on the random initial assignment in the step 1. Now this time we randomly assign the membership again, but this time we assign differently, right? And then we will repeat that, and we have the final results. And we repeat that multiple times and choose the one that gives us the best results. Okay, so that's how we do it in the K-means. Okay, now let's see an example. So this is the human tumor microarray example. So the data contains many rows. Okay, each row is a gene, but we have 64 columns. 64 columns. Each column means a patient, represents a patient. Okay, so here we use the color, the red and green and black, to represent the gene expression levels. Okay. If it's red, that means it's above the average. If it's green, means it's below the average. If it's black, that means it's close to the average. Okay? So each sample has a label. So among these 64 patients, they have different types of cancers, like the breast cancer, melanoma, and so on. So here we run the K-means. Okay, so we try the K-means with the K range from 1 through 10. Okay, so here I'm only showing a subset of genes on 64 patients. So I only showed a subset. Okay, so this is the results. So here, this is the k-means. I tried the k from 1 through 10. Okay, so this is k is 1, 2, 3, and 10. Okay, so and this is the within cluster variations. So you can see when the k increases, that decreases. Okay, so here I'm just showing you the k when the k is 3. This is the results. So although when we do the cluster analysis, those patients' cancer status is not used in the cluster analysis. So when we run the clustering, k-means clustering, we only use these gene expression levels to do the cluster analysis. But when we show the results, I included the patient's cancer status. Okay, so that you can see if these cluster analysis results make sense or not. Okay, so that can show you that if the cluster analysis is useful or not. Okay, but just keep in mind when we run the k-means, it does not use the patient's cancer information. It only uses their gene expression levels. So you can see here we have 3 clusters because we choose the k is 3. Okay, so you can see for the breast cancer, you can see we don't have a good separation because the cluster 1 has 3 patients for breast cancer, cluster 2 has 2 patients, cluster 3 has 2 patients. See that? For the breast cancer, the cluster analysis doesn't give us a good separation. However, when we look at the other cancer, like this is the colon cancer, I think. So we have 500. Oh no, this is the colon cancer. This is CMS. I forgot what that means. So we have 500. So that means the cluster 1 really includes all the patients with CNS. And for the colon cancer, that's all in the cluster 3. For the K562, they are all in the cluster 2. For the leukemia, cluster 2. MCF7 in the cluster 2, and so on. So you can see that does shows that those clusters actually only use their gene expression informations, does give us some interpretable and meaningful results. Although the breast cancer seems to be not informative, but for the others, we do see some very clear separation, right? And interestingly, here, although for the breast cancer, doesn't show much later after we done this analysis, and then the investigator re-look at the data set. They found that the 2 breast cancer in the second cluster were later found to be misdiagnosed, and they were actually melanomas. Okay, and you you can see for the melanomas, we have 8 and 7 of them in the cluster 2. And actually, if we add these 2 to here, so we will have 9 melanoma patients in the cluster 2. Only 1 is in the cluster 1. Okay, so that does show some very useful and informative results based on the cluster analysis. And remember, that is unsupervised learning. We didn't use the cancer information to do the cluster, but actually the results does shows good separations among 3 clusters for these cancers. Okay, so that's the human tumor microarray. So simulation 1, this is a simulation study. Okay, so why do a simulation study? The reason is that the simulation, when we run the simulation, we know the underlying truth. Okay, so here I created this data by myself. So I know that when I create this, I used two normal distributions to generate this. One is the red triangles. These are generated using the mean is, this is a bivariate normal distribution. That means we have two variables, x and y. I use the mean for the center is 0 and 0. Okay, so in other words, when I generate this data by myself, the mean that I choose for this data is based on a bivariate normal distribution with the mean at x is 0, y is 0. And when I generate these data, I used a bivariate normal distribution with the mean equals to 1 for the x and 1 for the y. Okay, so these are the mechanism, underlying mechanism that I generate the data. Now, when I do the cluster analysis, okay, using the k-means, I just pretend that I don't know this membership. Okay, so I don't know this membership. I just have this x and y coordinates information and then run the k-means. Okay, so I generated these 100 data points, and this is the code to do the to get the to generate the data. And then I use the k-means. K-means function in the R, that's the function to do the k-means cluster. And you need to specify the k. So to specify the k, that's the centers equals to 2. That means k is 2. Okay, so I run that, and you can see now it shows me the results. That's the k-means clustering with 2 clusters. And the size is 51 and 49. And that means 51 subjects into the cluster 1 and the 49 into cluster 2. Okay, and this is the mean for the 2 clusters. And you can see here, the first cluster has the mean equals to what? X is very close to 1. Y is also very close to 1. Remember, when I generate this data, I actually generate this using the 1 and 1 for the for for this data. For the black circle, I used 1 and 1. And you can see the cluster means are very close. This is the centroid for the cluster 1. Okay, and for the centroid for cluster 2, that's very close to 0, 0. You can see x and y, and in the reality, when I generate this, I use 0 and 0. So you can see that using the k-means does reflect the underlying true values that I use to generate this data. And the cluster vector. So here I showed, I give it, I have 100 data points, and this is the membership status. So you can see the first 49 subjects are from cluster 2, and the rest of the 51s are from cluster 1. Okay, and this shows the within cluster sum of squares by the clusters. So that is the within cluster from the cluster 1, and this is within cluster from the cluster 2. And these two numbers, how do we get these numbers? If you go back, so we have 2 clusters, so k is 2. So for the cluster 1, that is find out by using this. So this is the pairwise distance, take the square and do all the summations in the cluster 1. Okay, and for the cluster 2, we do the same thing and divide by 2. Okay, so that's how we calculate these numbers for the within cluster variation numbers. Okay, and then between sum of squares slash total sum of squares, that's 75.5%. Okay, so what does that mean? That means, so this is very similar to the analysis of variance. Okay, so what it tells us is that the first one is the denominator is the total sum of squares distance. So total sum of squares distance is what? Is for all these data points, we just consider as one single group. And then we measure the summation for all the pairwise distance. Is that clear? So like that includes like, for example, this point to this point, we have a point pairwise distance, and these to these to these. So some of them are within the cluster, some of them are between the cluster. But anyway, we just find out all the pairwise distance using all the data points. And that we get a total sum of squares. Is that clear? And then what's the numerator? Numerator is the between sum of squares. So what is between sum of squares? Between sum of squares is only measuring for this one. We are measuring the sum of squares for this one to all the samples not from the same group. So for this particular observation, we find out the pairwise distance to all the subjects not in the red group, but in the black group. So we get all these, we find out the total sum of squares. Is that clear? And then we do the same thing for the others. And then also we do, so we measure that. And mathematically, we can prove that, so here, the total sum of squares can be decomposed into 2 parts. That's the between sum of squares plus within sum of squares. Okay, so what does that mean? That means the total sum of squares, that's if we combine all the data points as one group and measuring all the pairwise distance, take the summation. That sum can be break into 2 parts. One part is the between sum of squares. That's the sum of squares for each observation to all the observation not in that group. Plus the within sum of squares is what? Is all the pairwise distance to its own members within the same group. Is that clear? So that means if that proportion is very large, that means what? That means the cluster result is good. That means the most of the variations are coming from between cluster variations. Is that clear? That means most of the variation are come from the distance between 2 subjects that are not from the same group. So this is kind of like R square in the regression analysis. Okay, why? Because this is between 0 and 1, just like R square. When the R square is larger, it's close to 1, that means perfect. When it's close to 0, that means it's useless, right? So here, what it says is that if the proportion is large, that means most of the distance is coming from the subjects between two different groups. Okay, so the larger, the better. So keep in mind that what is cluster analysis? The cluster analysis, the purpose is very, very simple. Is trying to find out what? Trying to find out, here, I think I should, I didn't, is trying to find out all the subjects within the same cluster are more what? Are more homogeneous. All the subjects between two different clusters are less homogeneous, are very different. So that's the purpose for the cluster analysis. So that's why the proportion for the between sum of squares over total sum of squares, if that is large, that means what? That means all the subjects within the same cluster are more homogeneous, are more similar to each other. And the most of the difference are mainly from the subjects in two different clusters. So that's exactly the purpose of cluster analysis. So that's why that part, the larger, the better. So here we have 75.5. Okay, so which means that's good. Okay, for the simulation two. So I think let's stop here. So we can continue next time. So any questions? Okay, so if you don't have any question, let's stop here.